I'm Anil Kumar. Welcome to my series on advanced algebra. We'll now look into a very important concept, which is proof by contradiction. I've taken 6 examples in this video. These are very popular test questions normally seen in any of the test paper. So I hope their solution will definitely help you. So the question here is to prove each of the following by contradiction. So whenever we're trying to do it, you will always see that the statements are correct. Now, we have to prove them that they are correct. So that is the whole idea, right? So let's look into these statements. Question number one is there are infinite prime numbers. Question number two is there are no positive integer solutions to the equation x squared minus y squared equals to 1. Question 3 is there is no integer solution to the equation 8x plus 6y equals to 1. Question number 4 is if n squared is even integer, then n is also an even integer. Question number 5 is square root of 2 is irrational number. Question number 6 is tangent to circle is at right angles to the radius. All are correct statements. How do we prove that they are correct? So we are going to prove it by contradiction, and the here steps will be that you make an assumption, and the assumption will be that the statement is wrong. So you say, well, the statement could be true or false, correct? So we say assumption is that the statement is incorrect. So we'll say that the proposition or the statement or the rule is incorrect. So once we take that proposition, then we do some steps to show that that results into contradiction. Of any kind, right? So contradiction of some type. So since we come to a step where we are contradicting what we assumed, it is leading to wrong things. That means that the assumption was wrong. And then we say, well, since the assumption was wrong, the statement was correct, right? So that means we approved the statement. Or the rule, right? As the case may be. So these are going to be our steps to follow. And these are very logical steps used by well-known mathematicians. The very first example was taken by Euclid. So let's begin with that itself. As I was saying, question number one here is there are infinite prime numbers. Now this solution was provided by Euclid, and this strategy is extensively used. So the statement here is there are infinite prime numbers. So when we are saying infinite prime numbers, what could we say about the assumption? So we'll assume the other way, right? So the assumption here is not infinite prime numbers. Clearly, we're looking for finite set of prime numbers, correct? So that becomes our assumption, and we'll work on this assumption. We'll say, okay, so let this set be P1, P2, P3. These are prime numbers up to, let's say, Pn. So these are finite set of prime numbers. Now, if I have a number Q, which is product of all these prime numbers, P1, P2, P3, and so on till Pn, And if I add 1 to this, what happens? That results into a prime number. Do you see that? Since whatever is this number, which is q, it is not divisible by the previous prime numbers. That means it is a prime number. We have a remainder 1. And we also know that q is greater than pn, right? So we contradict our assumption. Since we have a prime number which is beyond the list of our defined set of prime numbers, and since we have contradicted, we can now say that the statement is correct. Since assumption led to contradiction. Do you see that? So that is how we could prove by contradiction that the statement is correct. Perfect. So I hope you got the concept. Now let's try to answer more questions. At this stage, I'd like you to pause the video and answer, and then look into my suggestions. Now, question number 2 is there are no positive integer solutions to the equation, which is x squared minus y squared equals to 1. We are saying there are no positive integers. Positive means greater than 0, right? So our assumption is there are, right? We say assumption is let a and b be positive integers as solution. Perfect. So we say this statement is true or false. Let us assume the other way, that there are positive integers a and b. In that case, a square minus b square will be equal to 1, correct? And definitely, since 1 is positive, we can also say that a is greater than b, right? Okay. Now, in this particular case, we could factor this. So we get a plus b times a minus b equals to 1. And what product of two numbers is 1. That means both should be 1, right? So that means a plus b equals to 1 and a minus b is also equal to 1. Now this statement is true when a is equal to what? So both are 1, right? I wrote 0 here. So both are 1. That means a is equals to 1 and b equals to 0. Perfect. You could get it like this also. When you add them up, you get 2a equals to 2, and that means a equals to 1. Correct? So if a is 1, b has to be 0. Substituting in any of these values, we know b is 1 minus a minus 1, right? So which will be 1 minus 1 equals to 0. So you could do like this also. So in any case, you led to a condition that b is 0. Now, that is contradictory. We are saying that a and b are positive integers, right? So we are contradicting. So b equals to 0 contradicts our assumption, right? So the assumption is correct, incorrect, and statement is correct. So we can say a statement is proved because of above contradiction. Clear? So that is how you could actually prove this. Now let's take up next example, which is question number 3. It says there are no integer solutions to the equation 8x plus 6y equals to 1. Okay. So we'll assume that there are, right? So let's say a and b are integers. We say integer solutions to the equation. Correct? So we are saying contradiction. Well, let a and b be integer solution. In that case, we'll get 8a plus 6b equals to 1. Well, I could factor 2, so we get 4a plus 3b equals to 1, and that gives you 4a plus 3b equals to half. Now, in this case, what we have here is an integer, and what we have here is not an integer. It's a rational number, it's a fraction. Perfect. And that is a contradiction. We cannot have an integer equal to a rational number. Correct? So again, from contradiction, of our assumption, we prove the statement. So that kind of logic can be provided. So I hope that makes sense, right? Question number 4 here is, if n square is even integer, then n is also an even integer. So again, what will you assume? Let n, we can say, let n be odd integer. See, if n square is even integer, then n is also even integer. We are saying n is also an even integer. We are contradicting to this and saying let n be the odd integer. In that case, we have n being odd integer. So that means odd integer will be like 2n plus 1, right? So that square, we want that to be even. But when you really open this up, what do you get? You get 4n squared plus 2ab, which is 4n plus 1. Well, that is not even. Perfect. So it is not even. That means a contradiction to our assumption. Clear? So clearly, we can say that the statement is correct. That is, n should be an even integer. If n square is an even integer. Clear? So that is how we are going to prove it. Let's take another example. Square root of 2 is irrational number. Now we know square root of 2 is irrational, but we need to prove it. How do we prove it? By contradiction. So see the beauty. So we are saying let our assumption here is again reverse of what we are trying to say. Assumption is let square root 2 be a rational number, not irrational, rational. So as soon as I say rational number, we can say square root 2 could be written as p over q, where q is not equal to 0. That is what you mean, right? It's a rational number. Now, if square root of 2 is equal to p over q, then square both sides, we get p square over q square, or we can say 2q square is equals to p square. Now, since we have 2 times q square, it means what? It means p square is even. So this means p square is even. Correct? Now, if p square is even, then we just showed in the last example that if n square is even, in that case n is also even, right? So in that case n is also even. So that means p is also even. So we could write p as equals to 2 times some other number. Let's say 2 times a, because p is also even. And substitute this value in our equation. So we are going to substitute this value, p equals to 2a, in our equation. So what do we get? We get 2q square equals to 2a whole square, which is 4a square. Now that means that q square is equal to 2a square, means q square is even. And that means q is even. Correct? So that means both p and q are even, right? Perfect. Which is a contradiction. Since when we were saying that square root of 2 is equals to p over q, then p and q do not have any common factor, right? So they do not have any common factor. But here both being even, so both p and q are even, means assumption is wrong. Correct? Since p over q should not have any common factor, p and q should not have 2 as your common factor. And therefore, from again contradiction, we have shown that square root of 2 is irrational number. It cannot be written as p over q. You got the idea, right? So that is how we are going to show it. So in this particular example, we have made use of what we proved earlier in question number 4. Let's move on and take question number 6, which is also the last question in this particular video. Tangent to a circle is at right angle to the radius. So we have a circle, let's say O, radius R. We want to say that this is right angle for any line L, which is tangent to a circle. Now, a couple of important things to understand in this particular case. Now, since let's say this is the point P, O and P, so we are saying that OP is at right angles to, let's say, the line L. Let's call these points as, let's say, line L. Okay. Now, the question is, how do we prove it? We'll use contradiction to prove it. So we'll say let it not be perpendicular, right? So we say let OP be greater than 90 degrees or OP be less than 90 degrees, right? So OP is not equal to 90 degrees. So we are saying basically let OP be not equal to 90 degrees. Is that clear to you? Correct? In that case, what happens? Well, think like this. We have this particular situation, right? So OP is not 90 degrees. Let's say OP is something like this. This is O and this is P. And definitely this is not 90. So in that case, there will be some point M which will be at 90 degrees to the radius, right? So there will be some point which will be at 90 degrees. So that means this implies that there will be M at 90 degrees to the line. There will be M, OM, let's write. So from the center, I could have a point M, which is at 90 degrees. So in that case, OP becomes the hypotenuse. Correct? If this is 90 degrees, then OP becomes the hypotenuse. So that means that OP is greater than OM. It is something like this, that you're looking for a point somewhere there, right? If it is not at 90 degrees, it is somewhere there, right? Which is greater than the one which is at 90 degrees, which is a contradiction. We know that tangent and radius should be the shortest distance. This is actually the shortest distance. And if it is not 90 degrees, it cannot be the shortest distance. You get the idea. So if it is not 90 degrees, it cannot be a shortest distance. And therefore, from contradiction, we can say that tangent should be at right angles to the radius. Perfect. So once again, we have shown with contradiction how to prove our statements. So I hope that makes sense. So with the help of this particular set of examples, we have taken wide variety of questions, and that is what is expected for you to know at least. And I hope with this gives you a good background to answer similar questions. Thanks for your time and all the best.